In Chapter 1, Section 6, one of the PowerPoint slides has an example where in the solution of the problem that's in the slide, the answers are given. And on this particular slide, it says to check for extraneous solutions. And so in the example, we went through the steps to square both sides of the equation and then use combining like terms to isolate all the variables on one side and set the function equal to 0. And then we used quadratics techniques to get two values of x, x of 6 and x of 1. And then it says, well, make sure that those will work in the original equation. And they say at the bottom that 1 is an extraneous solution. And they don't really tell us much more than that. So I thought I would just elaborate a little bit on this particular problem on my pad. And let's see here if we can get this out of the way and get us a full screen here. And get this and this out of the way. I think we're done now. All right, so this is in 1.6, and it was the comment about extraneous solutions. And what we've been doing is we've been squaring both sides of the radical, and you saw the steps, I hope, on the slide where they squared this, and they wound up getting a couple of values. They said that the values were x equal 1 and x equals 6 were the solutions that they had on the slide. Now, that the reason they rejected x equal 1 is easier. It's easier to see if you will use and look at the second step in the problem solution where they made this change and subtracted the 3 from both sides. Now, if you look at this version and say to yourself, well, what if I let x equal 1 here? 1 plus 3, 4, the square root of 4, which is 2, equals 1 minus 3, which is minus 2. Now, yes, the square root of 4 is equal also to minus 2. However, as a general rule, we're going to require that all of our even roots be positive values. And so we're going to exclude, for the most part, we're going to exclude these negative answers. Now, that's going to change a little bit when we start looking at solutions to quadratic equations, because we will wind up using both the positive and the negative roots to find the values that make a function equal to 0. But for these equations, they want us to just limit our answers to positive roots. So that may help you a little bit understand how an extraneous solution comes about. The way they checked it is they just went back to this version of the equation. They came down and they said, well, that 5 does not equal to 1. Well, that's true, 5 doesn't equal 1, but it's easier to see why the solution of 1 is considered extraneous because of this example here, where we say that the square root of 4 is in fact equal to minus 2. So that is correct. However, for these equations, we want to require all of the even roots to be positive. One other thing they didn't mention is if you look at this radical, you can tell that whatever values of x we get, they've got to be what? Greater than or equal to minus 3. Why? Because if it's minus 3, then minus 3 plus 3 is 0, and the square root of 0 is 0. I'm not saying that's a solution. I'm saying that's a limit on the domain for x. If, for example, you let x be something smaller than minus 3, like minus 5, or minus 4 even, you're going to get a negative value in this radical, then we won't be in the real world, right? So we'll have something like minus 5 plus 3. Well, the square root of minus 2 would be I. It would be I times the square root of 2. So we would not be in a real world solution there. So anyhow, there should be some other statement about a restriction on the domain for x on this. Okay, so I hope that helps you a little bit about understanding what do they mean by an extraneous solution.